Well, this is the second recording for Physics 122 Unit 12. It's actually from a certain point of view, it's the third recording. First time I did it and several other of the recordings for this part of the course accidentally got deleted at one point. So I re-recorded it, and this particular video came out without any sound. So this is a re-recording, and if this one doesn't work, I'm going to be irritated. But anyhow, this is the second part of section 12, and where we left off, I bet you'd like that this way. I had been talking about, actually, I think I was a little further down the page. Down in here someplace. So it was interference of waves, how that if two or more waves line up with each other, they reinforce and you get a larger amplitude, making sound louder or light brighter. And if they're out of phase with each other, then they cancel and you get a low brightness or a low loudness. And the last thing I'd done was go through this example here, where this ray was exactly 1.5 wavelengths longer than that ray coming from, see, this is a barrier with two slits in it, two little openings. The waves pass through those openings and diffract, which makes them spread out in all directions so that they overlap and interfere with each other. And because this path is a wavelength and a half longer than this one, it throws them out of step, and that's why you get cancellation at this point on the screen. So if the screen is very far away compared to the distance between the slits, like if from there to there is maybe 1/10 of a millimeter, and if from the slits to the screen is like a meter or two, so that's like 10,000 times as far, then these rays are pretty close to parallel to each other, which makes this triangle here pretty close to a right triangle, which means we can do a little bit of trigonometry to get an expression for the path difference, which I labeled on this version of the diagram over here. So from there to there is how much longer this ray is compared to that one. And if this angle in the corner is very close to being 90 degrees, then this angle up here in the top of the triangle would be the same as this angle theta between the rays and a perpendicular to the plane containing the slits. So this theta here is, for all practical purposes, equal to this theta up in the top of the triangle, which means our path difference is the opposite side of the triangle, which means it's equal to d sine of theta. Hypotenuse times sine gives you the opposite side of a triangle. So if that path difference is equal to a whole number of wavelengths, you get constructive interference. And if that path difference is a whole number of wavelengths plus an extra half, then you get cancellation, as I explained in the previous video. And that path difference again would be equal to d sine of theta if the screen is very far away. If it's quite close, then the idea of this being equal to d sine theta breaks down. So having said that, there are these two problems for you to work on. So you should know the routine by now. You're supposed to pause the video and work on these, see if you can do it yourself. And when you come back, I will talk you through it. I'm going to pause it for a moment myself here, if I can remember. That one right there. Okay, I'm back, and so are you. So Number two, I deliberately threw in an obsolete unit here because even though it's officially obsolete, people still use it all the time. I've read magazine articles probably within the last month, where I saw the word micron, even though supposedly decades ago somebody decided you shouldn't say that anymore. But old habits die hard. A micron, as I wrote here, the modern thing to call it is a micrometer, 10 to the minus 6 of a meter. So the question says that the slits, okay, maybe I should begin at the beginning. It says the first order maximum. In other words, we're talking about one of the bright areas in this interference pattern. So you look at your formula sheet, or you look at the notes right here, and where you get constructive interference, which is what would give you maximum brightness, d sine theta equals m lambda. So write it down and then start sticking stuff into it. D means the distance between the slits, like I showed in the diagram right there. It's supposed to be the distance from this slit to that one. So 50 micrometers, micro means 10 to the negative 6. Theta is the angle that we're going to solve for. M is the order number. The question says this is the first order maximum in the pattern. In other words, this is where you have constructive interference because these two rays differ by one wavelength. If it was the second order maximum, that's where they differ by two wavelengths and so on. So one for M, and then the wavelength 380 nanometers. Nano means 10 to the minus 9. And if you don't happen to remember that, there's a place on the formula sheet where you can look it up. So once you've got all that written down, the rest is just crunching through the math. I converted things. You don't actually have to. I mean, any calculator that I'm familiar with will accept a number in non-standard form like this. Scientific notation, normally, the coefficient is supposed to be in the range of 1 through 10. And so that's what I did, is 380 times 10 to the negative 9. What would make a math teacher a lot happier is if you called that 3.8 times 10 to the negative 7. Same thing here. I converted the 50 microns. But a calculator, I'm pretty sure, will actually accept. You don't have to convert it. It'll take it this way. Anyhow, you divide, and that doesn't give you the angle itself. It gives you the sine of the angle. To get the angle itself, you have to take the inverse sine of that. Because if you take, maybe I should write that out in a little more detail. You've got sine theta equals 0.0076. Well, sine and inverse sine are inverse functions of each other. That's why it's called the inverse sine. And inverse functions always kill each other off. So like if you take the square of a square root, you just have the original number. And in the same way, if you take the inverse sine of both sides of this equation, over here, inverse sine and sine cancel each other out. And then you punch that up and that'll be theta. That'll be the answer. On pretty much every calculator in the world, that would be second function sine. And if you're not getting I guess it's up here, 0.435, One other thing I would suggest is that you make sure your calculator is in degree mode, because I've used a lot of red ink over the years on people who thought they were calculating something in degrees, but their calculator was actually in radian mode. And so that's something to be careful of. So then number 3, if you haven't already done it, pause it. And there's another look at it again. Comes out a little fuzzy, but I think you can read it. If not, well, there's places you can get a clearer look at this. Course's website. Anyhow, it says the pattern from the previous question, the one where the angle was 0.4 something of a degree, is projected onto a wall 2.5. So that would be the distance from here to here, 2.5 meters away from where the slits are. So if the 0th and the first order maxima, back up here on this picture, it's bright here and it's bright here, and the question's asking for the distance from there to there. Or on this thing here, it's asking for the distance like from there to there. Anyway, this is actually more of a, oh, now the focus is doing its little throbby thing. That's kind of annoying. Okay, this is actually a math problem rather than a physics problem exactly. You have to do a little bit of right triangle trigonometry and solve for this side of the triangle if you haven't already. So I'm going to assume you've given it your best shot, and now I should talk you through it. So this blob of ink here is supposed to be a bright area, and this blob of ink here is supposed to be the next bright area, and this would be the first order on the other side of the center. So we're looking for the distance from there to there, which the letter Y seemed like as good a choice as any to give it a name. We know from number 2 that this angle is 0.435 of a degree, and this distance was given in the question. And so since we know the adjacent side and are looking for the opposite side, that suggests using the tangent function, because tangent's opposite over adjacent. You look at the picture, the opposite side is y, the adjacent side is this, 2.5 meters. To solve for y, you multiply both sides by 2.5, you punch that up, and the distance comes out 1.9 centimeters. Let's see what's on the next page. Something exciting, I'm sure. Now we're going to talk about diffraction gratings. So what if instead of having just one pair, or just 2 slits, one pair of slits, what if you had many? So you've got a barrier, and there's a little gap there where some waves can get through, and screen is over here, and yeah, that's a nice straight line, isn't it? Anyway, we're interested in this point on the screen here, and this ray comes from that slit, and that ray comes from that slit. And I probably really should have used a ruler, but if it's bright, then m lambda equals d sine of theta. Well, what if there's a third opening, and there's a ray that goes through that to that same point on the screen? Well, let's say, just for the sake of talking about it, that maybe this is the first order maximum here, m is equal to 1, which means this ray is 1 wavelength longer than that one. Well, the slits are equally spaced, so this ray is also 1 wavelength longer than that one, which means this one is 2 wavelengths longer than this one. And so everybody's all lined up real nice, and it makes constructive interference. And if you add yet another ray, then, well, this one differs from that one by 1, and it differs from that one by 2, and that differs from that one by 3. And those are all conditions that give you constructive interference. And so it's still going to be bright there. And you can keep on going like this until you have thousands of little openings in the barrier. And all of those thousands of rays are going to be lined up at this point. So you'll get a bright area at the exact same place you would if there was only 2 slits. But here's the difference. What if you go just a little bit to the side, where maybe this ray is 10 degrees out of phase with that one instead of being perfectly lined up with it? Well, 10 degrees out of phase is still pretty close to being lined up with each other. So the screen here is going to be almost, with just 2 slits, okay? Cover up all those other ones for a moment. With just 2 slits, the screen here is going to be almost as bright as it is there. And so with 2 slits, the maxima, you know, they're broad and fuzzy. It gradually gets brighter and brighter until it hits a maximum here, and then it gradually gets dimmer and dimmer again. If you go to 3 slits, well, this one is 20 degrees out of phase with that one, which is still fairly close to good alignment. But if you keep on adding slits, by the time you get to the 18th one down here somewhere, that ray is 180 degrees out of phase with this one and cancels it. And the ray through the 19th opening cancels this one, and the ray through the 20th opening so, you know, there's thousands of slits, and there's only a tiny amount of the light that doesn't have another ray that cancels it. So the point is, with thousands of slits, you still have a maximum in the same place, but if you deviate from that even a tiny bit, you get destructive interference, pretty much. So instead of it being, when it was 2 slits, it was constructive interference here, it was destructive interference there, and some in-between kind of interference just about everywhere else. But with many, many slits, it's constructive interference there and darkness everywhere else. You have just razor sharp maxima at that particular place. And that's what it says at the top of page 45. Many, by many I mean many, equally spaced parallel slits, or actually the way gratings are usually made is you don't actually have a hole that goes all the way through a barrier. They get a piece of glass and they put a lot of carefully placed scratches on it. And the way light is scattered by those scratches is equivalent to having them go through openings. It can either go through the glass, that would be a transmission grating, or it can reflect back off of the glass. That would be, you know, like a mirror with a lot of scratches on it. That'd be a reflection grating, and it's an equivalent situation to having a lot of openings in a barrier. So constructive interference at the same angles as with 2 slits, like it says right there, but it's dark if theta is even a little bit off, which means if you pass white light, which is a mixture of different wavelengths, through one of these things, well, different wavelengths will then be diffracted through different angles. Now, if you send your white light through a pair of slits, the maxima are broad and fuzzy, and the colors still overlap quite a bit. But with a grating, one wavelength gets laid down exactly there. A slightly different wavelength gets laid down exactly next to it, and so on and so on. Each wavelength has its own precise angle that it gets diffracted to, and so it separates the light out into a spectrum. except for the central maximum, because if m equals 0, theta equals 0, no matter what the wavelength is. So everything just lands on the screen right there. But for any of the side orders, the first order, like it shows on here, you've got violet on one end and red on the other and other colors in between. Further out from the center on the screen, the pattern repeats again in the second order spectrum. Maybe there'd even be a third order spectrum, or maybe not, depends on how the wavelength compares to the line spacing on the grating. So another one for you to work on. You don't really need to worry about the fact that it's a mercury vapor lamp that produces this particular wavelength. All you need to know is the wavelength, but well, little background information. That happens to be one of the lines in the spectrum of mercury vapor. So you have a mercury lamp, then you pass the light through a filter that weeds out all the other lines in the spectrum, and that's how you end up with this monochromatic light. And this is how many lines per centimeter have been scratched onto the grating. And just like in the previous example, you're looking for theta. So pause it, work on it. And here we go with the answers. No, haven't got to that one. Don't look at that. That's the wrong page. You're supposed to do that one later. That would be cheating. So number 4, that's the one I want. So the maxima, like it says up here, are where d sine theta equals m lambda. So question says, let's see. Well, I guess it doesn't actually use the maximum, the word maximum, but where the line is located is where you're getting constructive interference. Everywhere else, the screen is dark. So the maxima are here. Now, one thing that usually trips up some people is the spacing. They want to put 8,000 in there. No, it doesn't say 8,000. I mean, that would be a really big diffraction grating if you think of it. It's not 8,000 centimeters from one scratch to the next. It says you have 8,000 scratches per centimeter, which means the distance from one scratch to the next is 1/8,000th of a centimeter. Now, the unit on D and the unit on lambda have to be the same. They don't necessarily have to be meters. You could have them both in centimeters. You could have them both in nanometers. But what seemed easiest to me was just to get them both in terms of meters. And the easiest way to avoid moving the decimal point in the wrong direction seemed to me like if I converted it, if I divided it out, everyone's always moving when it's a fraction, everyone's always moving the decimal that way when it should go the other way. Maybe it's a little more obvious if you do it like this. So whether you want to call it 1/800,000th of a meter or 1.25 times 10 to the negative 6 meters, that's the distance from one scratch to the next on the grating. M is equal to 2 because it says to find the angle for the second order spectrum, and then 546 nanometers. Nano means 10 to the negative 9. So you do the math, and just like in the other example, dividing that out gives you the sine of the angle. You then have to take the inverse sine, and it comes out a little over 60 degrees. And then there's a second half to the question: does a third order exist? In other words, does the pattern repeat yet again somewhere over here and also somewhere down here? Well, the way to answer that question is to try and calculate where that third order spectrum is. And if you succeed, it's there. But when you repeat the same calculation using m equals 3 for the order number instead of m equals 2, you come out with the sine of theta equals 1.31. Well, the sine function for any angle is always somewhere between +1 and -1. Hopefully you picked up that little piece of trivia in some math class, so you can just look at that and say, no, there is no such thing as a sine that's equal to 1.3. But if you don't happen to remember that, go ahead and punch it up on your calculator, inverse sine, second function sine 1.31, and your calculator will yell at you for having tried to do that. So no, there is no third order. The second order is the last one in this case. Well, next thing on the menu, thin film interference. This is a different way of getting a couple of light rays that have traveled different distances, so they interfere with each other. Two-slit interference, you start with one original beam of light, parts of it pass through the two different slits, and from there are different distances to a certain point on the screen, and the difference in path lengths gives you interference effects. Well, this time, instead of diffracting the light through two different openings, we're going to create a path difference by reflecting the light off of some sort of a thin film. I've got a pair of binoculars right over there. I ought to, hold on. The thing I've got the camera on makes it hard to see where I don't want the, right. Okay, any kind of high quality optics are coated. The only time a lens is just bare glass is if it's in some sort of a toy. So I've got a pair of binoculars here as a handy example. And you may have noticed that with these or camera lenses or things like that, the glass has a little bit of a funny color to it. You see, it looks a little on the bluish or purplish side. And that's the coating that makes it look that way. So let me set this down. The purpose of the coating is to make the glass non-reflective. Okay, there are, I should get this pointed back at my, oh, wait a minute. There we go. It's going to throb again. Hold on while I make the focus behave. Okay, there are reasons. If you have just a bare piece of glass, like glass in that window over there to my left, I don't know the exact number. It's like maybe 10% of the light that hits it reflects off, and the other 90% goes through. So like you notice it more at night. You look in the window, you can see a reflection of yourself from the light that's bounced off of it. Somebody outside the house can see you too from the light that went through. So that's what's going on here, is you've got a light ray and it meets a boundary between one substance and another. And some of the ray bounces off, the majority of it goes on through. Well, if there's a thin layer of some kind of substance on top of the glass, the same thing happens again at the boundary between the coating and the glass. Once again, some light reflects off of the boundary and the majority of it goes on through. And then you see, this is supposed to look like your eye up here. You're looking down at the surface of this glass and you see down and back, there's your path difference. this ray travels that much further than this other ray over here did. And that's the path difference that gives you interference effects. Let's just stick to the case where the light ray comes right straight down perpendicular to the surface like that. Because, I mean, if it comes in at some sort of an angle like this, well, the same basic principle is still going on, but you have to bring a trig function into it and it gets more complicated. So let's for today just stick with the simplest possible case. And in that case, this ray, the one on the right, that one would just go right straight down and right straight back up. And 2 times t, where t is thickness for the coating, that would be the additional distance traveled by this ray compared to that one. So in this case, if 2t is equal to a whole number of wavelengths, that would give you constructive interference. But you say, I see an n. Why is there an n cluttering up the formula? Well, as it explains on the next page, the wavelength of light changes when it crosses over from one material into another. I'm trying to remember if I explained that in the next video. Well, it won't kill you to hear it twice. You can, if it's in the next video, you can just fast forward that part. But here's the boundary between, maybe this is air and this is glass. Speed of light in air is about roughly 3 times 10 to the 8 meters per second. The speed of light in glass is roughly 2 times 10 to the 8 meters per second. So here's some light waves approaching the surface of the glass. Now, here's the next wave. This one's already gotten into the glass. This one is now going 2 times 10 to the 8th meters per second. This one out here is still going 3 times 10 to the 8th meters per second. So until this one crosses over into the glass also, it's going to be catching up to this one because it's going faster. So you're going to have a shorter wavelength in the material with the slower speed of light. And of course, on the other side of the window, it would be the same thing in reverse. This one's going 3 times 10 to the 8th, so it's going to pull away from that one that's only going 2 times 10 to the 8th. The wavelength gets longer again. So what kind of interference occurs depends on how 2t compares to the wavelength in the substance, okay? And in the substance, the waves get shortened. At least the part I'm pointing at isn't on camera at the moment. So the wavelength in the substance here, how that compares to 2t, is what determines what kind of interference you get. And the wavelength in here gets shortened by a factor of n, the index of refraction, okay? N for glass is about 1.5. So the wavelength in glass would be about 2/3 the wavelength you have in air. So if you're going to use the wavelength in, well, actually lambda V stands for the wavelength in a vacuum, which is almost the same as the wavelength in air. The index of refraction of air is pretty close to 1. So when 2t, the path difference, is equal to a whole number of wavelengths in the material, you get constructive interference. Since the wavelength is changed by a factor of n, that's how n gets into the formula, okay? So The other factor is, and I'm sure I explained this in the next video, sometimes when a wave reflects off of something, it gets flipped upside down. Whether it gets flipped upside down or not depends on how the indices of refraction compare. So if you got if you've got light in glass reflecting off of air, it does not get flipped over. If you've got light in air reflecting off of glass, it does get flipped over. And so if one of the rays gets flipped and the other one doesn't, then that's going to switch which condition gives you constructive and destructive interference. In this case here, neither one of the rays gets flipped. Or if it was on the other side of the window where it's going from glass into air, then both of the rays get flipped and that balances out, and you'd get constructive interference where it's a whole number of wavelengths. If just one of them gets flipped, then that's this case here, where a whole number of wavelengths would give you destructive interference instead. So which formula gives you what depends on how the index of refraction of the film compares to the material that's on either side of it. And having said that, I'm pretty sure I've made it into what's covered on the next video, because the sound came out just fine in the third one. And yeah, I think I overlapped a little bit with it, but better that than to miss something.